Right. My name is Phil Hayes. I now work at the National Museum of Computing, which is at Bletchley Park, and I'm responsible for the running, maintenance and for the research on the wartime computer that was known as Colossus.
Could you describe what you've spoken about here at Code Mesh?
I basically try to tell the story of how the Colossus machine was required, why it was required, and the people behind the build of it, and the people behind the breaking of the cipher that the Colossus was used for.
Mm-hmm. Could you describe some of that history of the building of Colossus?
The original?
Yes, please.
It was designed by a chap by the name of Tommy Flowers. He was a GPO development engineer. The GPO was the forerunner of what BT is today, and his brief was to produce a machine that would do the mathematical calculation that was needed to break the cipher machine that was used by the German High Command. Now that machine is known as the Lorenz SF42. That was broken by a brilliant mathematician by the name of Bill Tutt, and it's his algorithms that are used in the first truly electronic digital computer, which is Colossus.
And how was your copy of Colossus built?
The rebuild?
Yes.
That is quite a long and complicated story, but basically the director of the project had worked at MI5. Mm-hmm. He had also been involved with the restoration of early British computers, and he found a paper relating to the story of Colossus, and that was in about 1990, and in 94 Tony was involved with the saving of Bletchley Park, which was where the Government Codes and Cipher School was during the war. Mm-hmm. That's forerunner of GCHQ today. Tony has been involved with restoring early British computers. He saw this paper mentioning Colossus, and Colossus is at Bletchley Park. He's involved with saving Bletchley Park, so he basically gets a team together to rebuild the machine.
Yeah.
Even though at the time all the information was still classified, but because Tony was ex-MI5, he had his clearance resurrected, and he was able to read some of the classified documents at the time. Mm-hmm. And that was how the rebuild all came about.
Is the construction of Colossus still classified, or?
That in itself is still a very complicated story. The machine itself, the hardware on the machine, the architecture of the machine, that was released in 2000 into the public domain, even though the rebuild actually started in 94. Mm-hmm. So this was after the rebuild. But we weren't allowed to talk about it. We were under quite some constraints from GCHQ, and we were not allowed to talk about it, even though we were rebuilding it. Those constraints really stayed in place to this 2000, when one of the documents was released, and just one document. And that is exactly what we talk about, the information that's contained in one document, and that relates to the hardware on the machine. That document only talks about one technique, and that is the technique that my talk is about, and that's the only one that's in the public domain today. The rest of the information, and there's a lot of it, is still classified today, and that's 2017.
How do you interact with Colossus?
Colossus is doing a pure statistical attack. Pure statistics. It's not based on doing a brute force attack, like German words. It's a German message that you're working on, so you're not doing a brute force attack purely because it will take too long.
Sure.
You do a brute force attack on Colossus, and that's the fastest machine at the time, will take in excess of 760,000 million years to do that brute force attack. But built up, when he broke this cipher all those years ago, he also worked out a mathematical way of teasing out the starting position of the wheels on the other ends that the operator set the machine to when he sent his original message. And it's those mathematical techniques that Colossus is using, and that is based on pure bit patterns, not characters. It takes too long. It's pure bit patterns, and you go from 760,000 million years doing a brute force down to 3 or 4 hours.
Yeah.
And what you're setting the machine up for is those bit patterns. You're asking the machine to recognize particular bit patterns, and every time it sees it, it will basically count it. So it counts the number of times it sees the pattern that it's looking for throughout the message. And that gives you a statistical figure, how many times you've seen what you look for. And what you're doing is looking for anomalies.
Yeah.
Anomalies being when the wheel positions that you're working on are wrong, you will get a flat random number of times you see what you're looking for. That's how encryption works. It doesn't, if you saw something unusual, it's the way it is. So it's flat random. However, the wheels that you're working on at the time, and it's not 12, it's too many, when the wheels are in the right position, what you will see is a very, very slight increase in your statistical results. And that indicates, nothing more, it indicates that you found the starting position of the wheels that you're working on.
Got it. So, am I correct in understanding that Colossus is not a, I guess what we would now call a general purpose computer?
Correct.
So it implements a specific algorithm.
Yes, it's basically what you're doing is you're setting up the pattern that you're looking for. That is done with switches, and what you're doing with those switches is configuring gates.
Yeah.
In hardware, basically. You are connecting gates together, just like in an array. You put your switches into the patterns that you want to see, and that will connect gates together to perform that function. So it's all done in real time. It's not a stored program machine. It is a pure switch program, and it's all done in real time. An example of why it's not a stored program. The message that I normally run on the machine is 6,000 characters in length. That's what we normally run. It's the original wartime message, or copy of the original. That is 6,000 characters long. Each character is made up of 5 bits. It's 5-bit code. So that's 30,000 bits. In 1941, it would take 2 valves per bit. So that is 60,000 valves to store the message.
Right.
60,000, I mean, Colossus is huge, and that's 2,500 valves.
Right.
60,000 valves, forget it.
So what's the maintenance burden for a machine like Colossus? Do you have someone going through all the time and replacing?
Well, someone is me. There's only me that does it now. Take you back during the war. These machines are on 24 hours a day. The whole of Bletchley Park, which is a code-breaking town, if you want. There's over 3,000 people working there at the end. And these machines are working 24 hours a day. There are 10 colossi at the end.
Yeah.
And they're working 24 hours a day, 7 days a week, producing code. It is quite a hot environment. It's a noisy environment, but those machines had to be reliable. Because if the machines weren't reliable, forget it. Because what you are doing is you are reading these very, very important encrypted messages. So you need a machine that's quick and reliable. And they were. And the reason that they were reliable was quite simply because they never turned the machines off. Valves are notoriously bad at reliability. And the reason is you keep turning the things on. turning them off is okay. It's turning them on.
Yeah.
So Tommy Flowers, who designed Colossus, even though Bletchley Park were very concerned about the number of valves, because the prototype had 1,500 valves, they were very, very concerned that this machine was going to be unreliable. Like Tommy Flowers knew through his previous work on electronic telephone exchanges that if you turn a valve on and you leave the damn thing on, you only have that problem once. You only turn it on once, you only have the problem once.
Sure.
So you alleviate all these problems. So it becomes very reliable.
Yeah.
The machine today, the rebuild, I can't leave it on 24 hours a day. One, because of the cost of electricity, and two, have to employ somebody there 24 hours a day, 7 days a week, because the machine is a fire hazard because of the amount of power it consumes. So what I have on the machine is what's known as variacs. Probably today people know it as soft start. These are electromechanical transformers, and when they're turned on, they bring up the power very slowly. So instead of switch, bang, you lose valves, bring them up nice and slowly, we don't have that problem. So over a year, I lose probably, very difficult to say, somewhere between 20, shall we say 60 valves a year.
Yeah.
Yeah, and I can cope with that.
Yeah, a manageable number.
It's a manageable number. They are original valves, not necessarily wartime. They're valves that were manufactured up to what, 70s, when all the manufacturing plant in the UK disappeared to America because no one wanted valves. So they are of original manufacture. Okay, they're not modern day valves. They are of original manufacture, and the design of the circuits is actually exactly the same as the wartime machine. So we haven't modified the machine.
So, do you have just a cache of spare valves?
Yeah. I have, present failure rate, I have somewhere in the region of 10 years spares. Now, when those spares run out, the machine will stop working. And the reason that it will stop working is because, yes, we could put some modern day electronics in there to replace the valves. But when we started out on this project, and it started in '94, the idea behind it was we build a rebuild of the original machine so that the public can not only see it, hear it, feel the heat and smell it. You know, it was there, it was the true machine. Now, if we were going to modify the electronics, to put modern day electronics in, the argument would have been all those years ago, let's get a front panel, few switches, few lights, PC behind it, job done.
Right.
Yeah? So if you start modifying it, you will say, well, let's get rid of all the electronics and put a PC and a few switches.
Right.
And that's why it will not be modified.